Hello everyone, we're the Architechs, united in our mission to illuminate the path to a sustainable future under the guidance of our esteemed professor, Ms. Jordana Shir Mohammed, or as we fondly call her, Ms. J. I am Mark Patrick St. Fleur, your team leader, here with Blake Jennifer, Gomez Jose, Minor Robin, and Shelton Joshua. Today we delve into the transformative world of renewable energy. As we explore these powerful alternatives, we invite you to envision a world where energy sustenance is in perfect harmony with nature, understanding that our collective efforts today shape the legacy of tomorrow.
Science behind renewable energy. What is renewable energy? Define renewable energy. Renewable energy is energy derived from natural sources that are replenished at a higher rate than they are consumed. Sunlight and wind, for example, are such sources that are constantly being replenished. Renewable energy sources history. Humans have been using renewable energy since the beginning of time to power rudimentary machines and tools, so its use and concept is not new. Early societies learned to harness the power of water, the wind, thermal springs, and the sun for daily life. Some of the earliest known wind-powered grain mills and water pumps in recorded history are by the Persians in AD 500-800 and by the Chinese in AD 1200. Until the mid-1800s, wood was the source of nearly all of the nation's energy needs for heating, cooking, and lighting. From the late 1800s until today, fossil fuels, coal, petroleum, and natural gas have been the primary sources of energy. Hydropower and wood were the most used renewable energy resources until the 1990s. Since then, U.S. energy consumption from biofuels, geothermal energy, solar energy, and wind energy have increased. Total U.S. renewable energy production and consumption reached record highs in 2022. Types of renewable energy and how they work. The main types of renewable energy that we use now and are most familiar with are bioenergy, solar energy, wind energy, geothermal energy, and hydropower. 1. Bioenergy, biomass energy. We can define biomass as renewable organic material that comes from plants and animals. Biomass contains stored chemical energy from the sun that is produced by plants through photosynthesis. Biomass can be burned directly for heat or converted to liquid and gaseous fuels through various processes. One process that we should all be familiar with is photosynthesis. Included below is a graph on how that process works. Biomass is typically converted in 4 different ways. Direct combustion, burning to produce heat. Thermochemical conversion to produce solid, gaseous, and liquid fuels. Chemical conversion to produce liquid fuels. And biological conversion to produce liquid and gaseous fuels. What is solar energy? How does it work? While solar energy seems to be the trendiest thing in renewable energy, the use of the sun for energy is not. One of the newer ways to use solar energy in this modern era is the solar panel. But how exactly do solar panels work? Solar photovoltaic PV devices or solar cells convert sunlight directly into electricity. Small PV cells can power calculators, watches, and other small electronic devices. Larger solar cells are grouped in PV panels, and PV panels are connected in arrays that can produce electricity for an entire house. A photovoltaic PV cell, commonly called a solar cell, is a non-mechanical device that converts sunlight directly into electricity. Some PV cells can convert artificial light into electricity. Sunlight is composed of photons, or particles of solar energy. These photons contain varying amounts of energy that correspond to the different wavelengths of the solar spectrum. A PV cell is made of semiconductor material. When photons strike a PV cell, they may reflect off the cell, pass through the cell, or be absorbed by the semiconductor material. Only the absorbed photons provide energy to generate electricity. When the semiconductor material absorbs enough sunlight, solar energy, electrons are dislodged from the material's atoms. Special treatment of the material's surface during manufacturing makes the front surface of the cell more receptive to the dislodged or free electrons so that the electrons naturally migrate to the surface of the cell. The flow of electricity in a solar cell. The movement of electrons, each carrying a negative charge, toward the front surface of the solar photovoltaic cell creates an imbalance of electrical charge between the cell's front and back surfaces. This imbalance in turn creates a voltage potential like the negative and positive terminals of a battery. Electrical conductors on the cell absorb the electrons. When the conductors are connected in an electrical circuit to an external load, such as a battery, electricity flows through the circuit. What is wind energy? How does it work? To harness the wind, windmills and turbines use blades to collect the wind's kinetic energy. Wind flows over the blades, creating lift, which causes the blades to turn. The blades are connected to a drive shaft that turns into an electric generator, which then generates electricity. Wind energy is actually a byproduct of the sun. The sun's uneven heating of the atmosphere, the Earth's irregular surfaces, mountains and valleys, and the planet's revolution around the sun all combine to create wind. What is geothermal energy? How does it work? Geothermal energy is heat within the Earth. The word geothermal comes from the Greek words geo, earth, and thermi, heat. Geothermal energy is a renewable energy source because heat is continuously produced inside the Earth. People use geothermal heat for bathing, for heating buildings, and for generating electricity. Some applications of geothermal energy use the Earth's temperatures near the surface, and others require drilling miles into the Earth. There are three main types of geothermal energy systems. 1. Direct use and district heating systems. 2. Geothermal power plants. Geothermal heat pumps.
Technology used in renewable energy sources. Hi, I'm Jennifer Blake, and my portion of today's topic introduces us to some of the technologies behind wind, geothermal, and tidal energy sources. Let's take a look together at some of these technologies and how they can work to deliver a cleaner and more sustainable future for all. Many technologies are used today in the industry of renewable energy, but for today's presentation, we will be focusing only on three of these: wind energy, tidal energy, geothermal energy. Wind power technology. Wind-powered technology is generally eco-friendly and does not emit harmful gases or emissions. This is incredibly important with the growing threat of climate change and global warming. The technology used for harnessing wind energy has been evolving over the years, from the early windmills in the 1950s to the advanced wind turbines being used today. The wind turbines we use today are large, tall structures with rotating blades that are designed to harness kinetic energy from the wind as they rotate, in order to generate electricity. To capture the stronger wind currents, the structure must be built at a high altitude. The wind flows over the turbine, creating a difference in air pressure that causes lift and drag on the blades. This causes the blades to spin, and a generator is connected to the rotor blades, speeding up its rotation. Energy is transferred to the generator as the blades turn. An electric current occurs inside the generator due to the changing magnetic field, creating electrical energy. The two basic wind turbine technologies that we use today are vertical axis turbines, horizontal axis turbines. The horizontal axis turbines are the ones most commonly seen populating a large landscape. These turbines usually have 3 or 4 blades. The blade is faced toward the wind in order for the blades to rotate. Vertical axis turbines do not need to be pointed directly into the wind in order to function. They can move in all directions and can be built on either land or water. Geothermal technology. Another form of renewable energy technology comes in the form of geothermal energy. Geothermal energy comes from the internal heat that naturally occurs under the Earth's surface. There are underground areas with intensely hot rocks and water that are heated naturally at a high temperature. Modern technology is used to harness the heat from under the surface, create steam, and power turbines to extract electricity. There are two main types of geothermal technology plants: flash steam plants, binary cycle power plants. For a binary cycle power plant, wells and pipes are drilled into the ground in order to access the hot rocks and fluids. When the fluid underground is heated, this is transferred to the surface through pipes and passed through a heat exchanger. Next, the heat from this fluid will be transferred into a secondary fluid, which will then be turned into steam or gas. This steam or gas can be now used to power a turbine. The steam creates the force that can cause the turbine blades to rotate. This is similar to wind turbine technology in that the turbine will be connected to a generator. As the generator is turned, electricity is created. This electricity will be transferred into power lines where it can then supply electricity to homes and industries. Flash steam plants are more common and are similar to binary cycle plants, but they use a rapid change from high pressure to low pressure to instantly change the fluids into vapor to power the turbine. This process can be done more than once in order to gain as much energy as possible. Tidal energy technology. Finally, let's discuss the technology used in creating tidal energy. Tidal energy has the benefit of being more predictable than other forms of sustainable energy. The rising and falling tides are always on schedule, making this a reliable form of renewable energy. The technology used to harness the kinetic energy from the tides is similar to the other forms of technology, in that a turbine is powered by the difference in water pressure, in order to rotate the blades of the turbine. Rotating the blades powers the generator, creating electricity. According to a 2014 IRENA Ocean Energy Technology Brief, there are three main types of technology used to harness the energy from the tides. Tidal range technology, tidal stream technology, hybrid application technology. Tidal range technology uses a barrier or dam built across the entrance to the tidal basin. The barrier can control and harness the movement of the water. Turbines are installed within the barrier and are designed to move with the rising and falling of the tides. As with the other forms of technology used to capture kinetic energy, the turbines power a generator, producing electricity. Tidal stream technologies differ in that they generate electricity by harnessing the horizontal movement of water from tidal currents to power their turbines. They can have horizontal and vertical axis turbines, similar to the ones commonly used in wind turbines. Similar to vertical axis turbines used in wind power, the vertical turbines are able to capture energy from currents flowing in any direction. This is due to the design of the turbine blades that rotate around the axis. The horizontal axis turbines are also similar to wind turbines. They are mounted horizontally on their axis, and the water flows past the blades, turning them. Finally, hybrid technology for tidal energy uses a mix of both tidal current and tidal range technologies in order to generate electricity. There are many more sources of renewable energy technologies that are not covered here today, such as solar, hydroelectric, hydrogen, and biomass. In order to preserve our planet for generations to come, we must properly utilize sustainable technologies like this in order to decrease our use of fossil fuels and combat the threat of global warming.
Engineering's transformative role in renewable energy. Ladies and gentlemen, today we'll embark on a journey through the fascinating world of renewable energy and the pivotal role that engineering innovations play in revolutionizing how we capture, store, and integrate renewable power sources. Section 1. Design and Structural Innovations. Let's begin with how engineering has harnessed the power of the sun, wind, and water. Imagine a world where solar panels are as efficient as the latest smartphone upgrades. Thanks to engineering innovations, we are getting closer to this reality. Solar photovoltaic (PV) systems have seen remarkable improvements, driven by innovative materials and sophisticated tracking systems. They've become akin to upgrading your smartphone to the latest model for better performance. But that's not all. Concentrated solar power (CSP) systems, those giant mirrors focusing sunlight, now efficiently store energy using molten salts, much like a solar-powered stove with advanced features. Now let's talk about wind energy. Picture wind turbine blades as efficient wind-catching sails on a ship. Engineers have designed longer blades that capture energy even from gentle breezes. Precise wind tracking, offshore turbines, and floating wind farms are expanding the horizons of wind energy, ensuring we harness it to its fullest potential. Hydroelectric power is another frontier of innovation. Modern engineering has optimized energy conversion from flowing water, much like refining the efficiency of a historic mill's water wheel. Energy storage, the backbone of renewable energy reliability, has seen incredible progress. Lithium-ion batteries, like those powering your smartphones, are dominating the scene, with ongoing research promising even greater capacity and faster charging. Smart technologies are working behind the scenes, much like the traffic management system in a city, ensuring that energy flows smoothly and reliably. And now let's not forget structural innovation. Engineers are designing floating solar and wind farms, acting as energy islands on water, minimizing land use and disruption to the environment. Moreover, renewable systems are seamlessly integrated into building designs, just as technology is embedded into our everyday lives, promoting sustainability and urban planning. In conclusion, engineering solutions have not only made renewable energy reliable, but also scalable, paving the way for a greener and more sustainable future. Section 2. Engineering aspects in renewable energy, infrastructure and grid systems. Our next stop takes us to the heart of renewable energy infrastructure and grid systems. Think of renewable energy sources as stars scattered across the sky. They need a sophisticated electrical grid infrastructure to bring their power to our homes and industries. Engineers have stepped in to create what we call smart grids, real-time traffic management systems for electricity. These grids are equipped with advanced sensors and control systems, allowing us to monitor and manage electricity generation and consumption in real time, enhancing reliability and accommodating the intermittent nature of renewable energy. Microgrids, on the other hand, are like backup generators for communities, ensuring power even during grid disruptions. Grid interconnection, in simpler terms, is like building efficient highway ramps to accommodate the flow of traffic seamlessly. Engineers make sure renewable energy sources smoothly integrate into the existing grid by optimizing interconnection points, considering voltage regulation and balancing loads. In the world of energy storage, think of batteries as energy reservoirs, storing excess energy for when we need it most. Pumped hydro storage, resembling the storage of water in a hilltop reservoir, is another method employed to store excess energy and generate electricity during high demand. Transmission infrastructure, our highways for electricity, is crucial for transporting renewable energy. High-voltage direct current HVDC lines act as high-speed trains, efficiently carrying power over long distances. Engineers are continuously expanding and reinforcing the existing transmission infrastructure, much like adding new lanes to a highway to accommodate more traffic. Grid expansion is akin to adding new lanes to a highway to accommodate more traffic. Engineers facilitate international and regional grid interconnections to share surplus renewable energy with regions in need, enhancing reliability, just like highways between countries allowing the exchange of resources. In conclusion, engineering innovations in infrastructure and grid systems, energy storage, and transmission infrastructure are pivotal for renewable energy integration. These advancements contribute to a reliable, resilient, and sustainable energy future, reducing carbon emissions and addressing climate change challenges. Section 3. Challenges and Solutions in Renewable Energy. Implementation and Engineering Perspective. Now let's explore the challenges and solutions in the implementation of renewable energy. Intermittency and variability pose a significant challenge. Picture solar and wind energy as somewhat unpredictable due to weather conditions. Engineers have responded with advanced energy storage and grid technologies, acting as the balancing act, mitigating intermittency. Grid integration, on the other hand, is like fitting pieces of a puzzle together. Integrating renewables into existing grids can be challenging due to different generation and demand patterns. Engineers are upgrading grid infrastructure, using high-voltage direct current (HVDC) transmission, and enhancing grid interconnection between regions to overcome this challenge. Efficiency and cost-effectiveness of energy storage are critical. Think of energy storage as a bridge, a savings account that stores energy for when it's needed. Ongoing research is focusing on improving storage technologies like solid-state batteries and thermal storage materials. Materials and manufacturing processes need to be sustainable. Imagine engineers exploring eco-friendly materials and sustainable manufacturing techniques, reducing the environmental footprint. Land and space constraints are a real concern. Large-scale installations impact ecosystems and compete for space. Engineers are innovating with vertical axis wind turbines, floating solar panels, and building integrated solar panels to optimize space. Environmental impact must be minimized. Some technologies like hydropower dams have environmental consequences. Engineers are developing mitigation strategies like fish-friendly turbines and habitat restoration. Finally, cost competitiveness is essential. Some renewables still struggle with cost competitiveness. Ongoing research, economies of scale, and policy support are driving down costs. In conclusion, engineers in collaboration with policymakers and researchers are working diligently to enhance the reliability, efficiency, and sustainability of renewable energy. As technology advances, renewable energy will dominate global energy demands while mitigating climate change. Ladies and gentlemen, today we've glimpsed into the powerful world of renewable energy and how engineering is shaping our future. As we navigate the challenges ahead, remember that these innovations bring us one step closer to a sustainable and cleaner world. Thank you for your attention.
Good morning. Today we'll look at the interesting world of renewable energy, concentrating on its efficiency, pricing, and future estimates. We'll use mathematical data analysis to investigate how renewable energy can be both an environmental and an economic boon. Efficiency of renewable energy. Data point. According to a study by Nadia Singh et al., an increase in renewable energy production leads to a 0.07% rise in output for developed countries and a 0.05% rise for developing countries. The research investigates the link between renewable energy output and economic growth in industrialized and emerging countries. The study reveals a positive and statistically significant influence of renewable energy on economic growth using the fully modified ordinary least square (FMOS) regression model, using data from 1995 to 2016. In particular, developed countries see a 0.07% increase in output, while underdeveloped countries see a 0.05% increase. The article also goes beyond GDP to explore other economic variables such as labor force participation and gross fixed capital formation. It emphasizes the critical necessity for a move to renewable energy as a result of the environmental challenges created by fossil fuels. The paper also highlights the urgency of transitioning to renewable energy sources due to the challenges posed by fossil fuel consumption, such as the growing mismatch between energy demand and supply, the threat of oil reserve exhaustion, and high levels of greenhouse gas emissions. The study suggests that both developed and developing countries are moving towards a green growth agenda, focusing on mainstreaming renewable energy technologies and creating a viable green energy market. This is seen as the next green revolution, aimed at reconciling high economic growth with an environmentally friendly development trajectory. By providing empirical evidence, the paper aims to influence policy decisions, encouraging a shift towards renewable energy as a driver of economic growth. It implies that policies should be designed to promote renewable energy technologies, which can contribute to economic variables such as employment and capital formation. Economic impact. A study by Q et al. confirms a reduction in ecological footprint due to an increase in renewable energy use across all income groups of countries. Global warming and tourism. The study discusses the issues of global warming and how it affects numerous industries, including tourism. Tourism contributes significantly to environmental damage, including tax and inclusion. Tourism economic imports. Tourism is $1 trillion that contributes 10% of global GDP and employs more than every country worldwide. However, there are environmental costs associated with it, such as pollution research. Tourism use. Tourism operations such as transportation, lodging, energy, increased carbon emissions. Air travel consumes 200 million tons per year. The levels, SDGs. The United States has goals 169% for sustainable development. The paper sets forth in the context of SDGs 6, 7, and 13, focusing on clean water, renewable energy, and climate action. Role of renewable energy. The paper suggests that renewable energy can mitigate the environmental impact of tourism. It can reduce CO2 emissions and treat sustainability standards. Positive impact of renewable energy. The paper underscores the potential of renewable energy in mitigating the environmental impact of tourism. By adopting renewable energy, the tourism industry can significantly reduce carbon footprint, contributing to global efforts against climate change. This aligns with the UN Sustainable Development Goals, particularly those related to clean energy and climate action. Moreover, the shift to renewable energy can also have economic benefits, such as job creation in the renewable energy sector. Future projections. Dynamic framework. The paper explores the complex relationship between renewable energy sources like hydroelectric, wind, solar PV, geothermal, and biomass power, and economic growth. It takes into account variables like capital, government spending, and trade openness. Methodology. Utilizing a heterogeneous approach for panel data and second-generation econometric tools, the study allows for cross-sectional reliance and slope heterogeneity. Feedback loop. According to Dumitrescu and Herland's research, there is a considerable feedback relationship between renewable energy sources and economic growth. This implies that investment in renewable energy can stimulate economic growth and vice versa. Global perspective. The research contributes to the current literature by evaluating the global picture of the energy industry, including energy demand and supply, as well as geopolitical variables influencing energy production. Energy future. By the end of 2050, renewable energy resources and energy efficiency are predicted to be the main indicators. The report emphasizes renewable energy's potential not only as an ecologically beneficial alternative, but also as a driver of economic growth. It implies that shifting to renewable energy can have two benefits: increasing economic growth and lowering CO2 emissions. This is consistent with global efforts to prevent climate change and ensure long-term prosperity. Renewable energy by the numbers. The International Renewable Energy Agency, IRENA, predicts that the global capacity for renewable energy will reach approximately 27999 GW by the year 2021. Solar energy has been experiencing a rapid growth in capacity, exhibiting an exponential trend. It is projected that the global installation of solar power would reach 714 GW by the conclusion of 2021. Wind energy is a significant factor in the global energy landscape, projected to reach a substantial capacity of 733 GW by the year 2021. Hydropower remains the preeminent renewable energy source, boasting a worldwide capacity of around 1211 GW as of 2021. According to a report by Bloomberg New Energy Finance, it is projected that the global investment in renewable energy would exceed $300 billion by the year 2020. According to the International Renewable Energy Agency, IRENA, the global workforce in the renewable energy industry amounted to over 11.5 million individuals in the year 2019. Renewable energy sources had a significant role in mitigating around 2.1 gigatons of carbon dioxide, CO2 emissions in the year 2019. In the year 2020, around 28% of the total worldwide electricity production was derived from renewable energy sources. Future projections, according to estimations, renewable energy sources are projected to account for around 50% of the global electricity generation by the year 2050. According to multiple assessments, the renewable energy sector has the potential to contribute over $100.7 trillion to the world economy by the year 2030. In conclusion, the quantitative study of renewable energy statistics presents a positive outlook. The utilization of alternative energy sources presents a comprehensive solution that encompasses both environmental sustainability and economic growth, rather than solely serving as a substitute for fossil fuels. As we progress, it is imperative to prioritize the formulation of policies that foster the generation and adoption of renewable energy sources.
Hello everyone, and welcome to this exploration into the innovative world of sustainable energy technologies. I'm Mark, and today I'm thrilled to guide you through a fascinating intersection of science, technology, engineering, and mathematics, also known as STEM, as we delve into two of the most promising environmental stewards of our generation, solar and biomass energy technologies. Technological approaches in renewable energy emphasizing solar and biomass energy technologies. The quest for sustainable, reliable, and environmentally friendly energy sources has led to an era where technological innovation is crucial in navigating the complexities of renewable energy generation. I aim to explore the multifaceted world of solar and biomass energy technologies, examining their current capacities, advancements, and potential challenges in promoting a sustainable energy future. While Jennifer has succinctly outlined wind, geothermal, and tidal energy technologies, my portion of this presentation seeks to examine solar and biomass energy technologies in depth. Solar energy, harnessing sunlight with advanced technologies. Photovoltaic systems, monocrystalline, polycrystalline, and thin-film solar cells. Each cell type offers unique trade-offs between efficiency, cost, and flexibility in applications, distinguished by their material and manufacturing processes. Perovskite solar cells. These cells promise high efficiency and lower production costs. but challenges such as durability and environmental stability require further research and development. Concentrated solar power, CSP. Technological variants. CSP technologies offer distinct capabilities in terms of grid stability and energy storage, including parabolic troughs, solar power towers, and dish engine systems. However, there are variations in cost and implementation feasibility. Biomass energy, leveraging organic matter for energy production. Bioenergy conversion. Conversion pathways. Biomass can be transformed into various energy forms through thermal, biochemical, and chemical conversion methods, each with its technical and environmental implications. Optimization challenges. Ensuring the efficiency and environmental soundness of these conversion processes remains crucial to maximize the net positive impact of biomass energy. Biogas technology. Anaerobic digestion. Biogas technologies leverage microbial processes to break down organic matter, providing energy production and waste management benefits. Co-digestion techniques. The amalgamation of varied organic waste types to optimize biogas production is emerging as a focal point for enhancing the viability of biogas technologies. Biofuel production. Generational shift. Subsequent generations of biofuels derived from non-food biomass and algae present a paradigm shift towards sustainability by mitigating the food versus fuel debate. Challenges and future prospects. Navigating through the technological landscape of solar and biomass energy, it is crucial to address inherent challenges and explore future prospects. While technological advancements promise enhanced efficiency and reduced costs, issues such as material scarcity for PV cells, land use dilemmas in biomass production, and the scalability of certain technologies remain pertinent. Emerging research in areas such as artificial photosynthesis for solar energy, genetically modified organisms for optimized biomass conversion, and innovations in energy storage technologies present a future where the integration and convergence of varied technologies could amplify the reliability and applicability of renewable energy sources. While technological advancements within solar and biomass energy generation present a promising trajectory towards sustainable energy futures, the journey is intertwined with challenges and opportunities for innovation. The examination and development of these technologies should consider the economic, environmental, and social dimensions of their implementation and operation. As we move forward into the era of renewable energy, the collective examination, knowledge sharing, and collaborative advancements in technologies such as solar and biomass will be crucial in steering our global society toward a sustainable, energy-secure future. In the context of technological advancements and the continuous evolution of renewable energy sources, how might the integration of artificial intelligence and machine learning technologies enhance the optimization, management, and utilization of solar and biomass energy? As we reach the conclusion of our journey through the innovative realms of renewable energy, it's essential to reflect on the critical insights and promising developments we've explored today. These technologies aren't just theoretical concepts or distant futures. They are active, evolving fields that continue to shape our world, our environmental response, and our collective future. Harnessing the sun's abundant energy and capitalizing on the renewable riches of biomass materials, we've seen firsthand how these technologies stand at the forefront of environmental sustainability. They challenge traditional energy paradigms and invite us to participate in a more responsible, resource-efficient era. We want to express our sincere gratitude for your attention and engagement throughout this presentation. It is my hope that the discussions ignited and the knowledge shared today will spark continued curiosity and dedicated action towards a greener, more sustainable world. Thank you once again, and especially Ms. J, for joining us on this enlightening exploration of renewable energy. Until next time, stay curious, stay inspired, and most importantly, stay committed to making a difference.